Jonas Seiler from Plista. Plista is a recommendation system in Germany, and he will be talking about online hyperparameter tuning in non-stationary environments. Welcome.
Yeah, thank you. As mentioned, Plista is actually doing news article recommendations. So when you read an article below, we present other articles you might be interested in, and also we put some ads in between so we earn some money. But today I want to talk about hyperparameter optimization, and so what's actually the problem? So the problem looks like this on the side here. So on the x-axis we have time. Actually, I'm actually sorry how the plot looks like. It looked better in the actual presentation. Converting to it, the PDF kind of messed it up. So what you see here is different oscillation going on. So you have here over one day this oscillation basically. So during the night people tend to click more than, the click rate is higher during the night than during the day. And also at the weekends the click rates are higher and then they crash from Sunday to Monday. So when you want to evaluate your hyperparameters, you have the problem that you have to run A/B test extensively. So you couldn't just run the A/B test for like a couple of days and then compare them with another A/B test afterwards, because if you evaluate them at the weekend, they are just a priori better than during the week. So what could you do about it? Also on top, in our special case, we have to deliver recommendations really, really fast. We have about 100 milliseconds to create the recommendations, so we extensively rely on caching. So we can actually run so many A/B tests in parallel because we don't have that much memory available to us. So what can we do about it? I want to start with the simple case of the hyperparameter selection, the offline case, and then we walk our way up to the actually more tougher case. So you're probably all familiar with the grid search. So here I just created a toy example. It doesn't mean anything. So you have two hypothetical parameters here. And so red basically means it's really, really good. Here in the right up corner, that would be the perfect parameter settings you're looking for. And the typical approach is for people, to just create a grid and run through it and search for the best hyperparameter. Another approach that actually turned out to be really, really good and actually been in most approaches actually better than grid search is random search. So where you just run through the search space randomly. So, for example, in this case, when you took 10 samples, so this plot basically shows the distribution of the metric for your parameters you've been choosing. So you see that after grid search versus random search, after 10 samples, you've been already collecting on average better parameters than grid search, and at the end of it, actually, you've been even able to find a little bit better sample than with grid search. The idea behind it, why random search can outperform grid search, is that you are only looking for the best parameter. You're not interested in actually to extensively search the entire parameter space. The only thing you need is one good example. And that depends on your landscape of your parameter space. If the space is big enough and you can then the probability, of course, just finding one good example is really, really high. If, of course, on the other hand, your parameter space is so tiny that you have to tune your algorithm so specifically to one parameter where it only works, well, then of course you have to extensively search for it. But on the other hand, if you have to so fine-tune your algorithm for one particular parameter, it probably means that your algorithm needs some tuning anyway. So I don't want to make I don't want to forget to say, I'm not saying random search is better than grid search. I'm just saying it probably finds your solution a little bit quicker. And also you can with it, you have kind of a random experiment for random search. So you sample points and you can see how your distribution changes over time. And you can kind of estimate with this when am I already finished? Am I found already a good solution? But actually, I don't want to make the point here that random search is better, or the thing you should do. Actually, what I want to say is how bad this actually is that we are talking about a random search. So we should definitely do something better than just randomly searching. So the idea is to build up now a model that we train on our parameter space, and we want to actually to calculate how much are we going to improve from parameters we haven't seen. So the model should actually then tell you which points to sample. There are very different metrics you can use. Here we present actually, or I want to present the expected improvement. Upper confidence bound is another, for example, popular metrics used. I don't think there is a reason to use one or the other one, and it's not, depending on how your data look like. So one will be perform a little bit better than the others, but I don't think that a priori one is better than the other ones. In our case, also later you see at the end of the talk that with the expected improvement and the mathematical definition, we can kind of nicely compute a result that is also, in specific cases, analytically traceable. So what is the improvement or expected improvement? So we have here our parameter that we found that's the best parameter so far we found, that's y star. So we take the distance to some other point y. If it's better than y star, this is then positive. If it was worse, so basically we want to maximize our parameters. Yeah, we have the distance just to the best point. And the expected improvement then is just really simple. It just tells us that we average over all y's that we have, and so basically our model here, by of x, tells us how likely is it that we're going to reach these level or these performance for a given hyperparameter. So what's a good model for P? You can use a lot of things. Commonly used are Gaussian processes. Gaussian processes have the nice advantage that they give you also not just a mean estimate of your parameter, but also a variance estimation, which is of course very useful for our purpose. So what is a Gaussian process? A Gaussian process is a collection of random variables, any finite number of which have a joint Gaussian distribution. Usually you only have to specify a mean function, which is usually just chosen to be 0, so you don't have to choose to do anything here, but just normalize your data so it has a mean value of 0. And the only thing you have to specify is a kernel function, which has to be positive semi-definite. Very common source is here the squared exponential, and it basically defines how similar points are to each other. The good thing also about this is what I showed you earlier here, these expected improvement. If you plug in here the Gaussian process for the expected improvement, this entire integral has an analytic solution, so you don't rely on numerical optimization. So in our previous example, how does it look like? So now we have here the random walk again, and this is the outcome of the expected improvement using sequential model-based optimization. That's what SMBO stands for. So what you see here, you have a nice distribution. It walks through the entire parameter space. It also looks, if you can see that, at the borders for optima, and in the end it just really looks in the spot where we want to and searches for the optimal parameters. Of course, also after 10 examples, it looked usually for better, on average, it looked in more, or found better solutions, and after 36 examples also, you see, I mean, the overall, it both found the best parameter, but on average, sequential model-based optimization found more, or searched in a space that is more valuable for us. So that was now actually the case when we have non-stationarity. So, oh yeah, forgot of course the most important part for you. Oh, thank you. Yeah, the most important part for you. How can you apply that? You don't have to do much actually. There's a nice framework implemented by, I think, Scott Clark is his name, not sure. He developed the framework in his PhD thesis. He works now at SIGOP and in between at Yelp. And they published Mo. It's a nice framework. It has a REST API. You can just query it with your templates you already had, and it basically gives out new samples that you are supposed to query. We, for example, at Plista use it and just combine it with the cross-validation from Spark, and so we can just speed up every cross-validation that we have and use with Spark. I can just highly recommend using it. So now let's talk about the non-stationary part. I have to say that all the kudos goes to my colleague Max Woyle, who derived most of the results in his master thesis. So if you want to look up for the details of it, please look up his master thesis. So what do I mean by non-stationary, or which kind of non-stationarities? A lot of kinds of non-stationarities. If you look up in the literature, usually it's also so you find like a constant slow drift, a fast drift, or periodic drift. So, and as you can see, also you can have multiple different kinds of stationarities in your data. As we have like constant shift, we have periodic ones, we have very sudden shifts. And the idea is basically to also put that into the model and then average out these non-stationarity. So in this example, for example, we wouldn't want to select these parameters -5 here. So again, here we would have the time axis. Here would be our hyperparameter, and you see the very best point you could get is here, but only for a very specific time point. So in principle, you would be more interested in a solution that is really stationary over time, this one. So how do we do this? So that was the old formulation we had, where we've been looking for a model that predicts the probability of y given x. So we now just kind of add our non-stationary parameter to it, so we call it t because usually it's time. And under mild assumptions, you can get to a very easy equation where you just have to know the prior probability of your non-stationarity parameter, and then you can average over it. The problem is, of course, depending on how your prior looks like, these integral is no longer, well, it doesn't have no longer an analytic solution, but you can use Markov chain Monte Carlo algorithms to approximate the solution. If you have a uniform prior, though, which, of course, for time is very common, you can derive such a solution so that you only have to integrate over the time variable of the Gaussian process, which has a solution which is pretty ugly, so I'm not putting it on here. So what I have now not told you is actually, of course, you need to model what's the best value as well, since it's non-stationary. Of course, the best value would be something like here, but it's unfair to always take this best point if you compare it during the week, right? So, of course, you could, of course, use just a global best point. It sometimes can work, but you probably, and that's what we do, is also come up with some sort of model for your best point. Often also very simple approach to approximate this integral is to just discretize time, and then you can basically just get this best point for point t very easily. Yeah, so let's come to an evaluation. So we evaluated on different data sets. So first is an synthetic one, the one I showed you already. And here the interesting point about it, that even though the best parameter is here, we actually are interested more in, so here the best parameter we actually want to have over time is somewhere here. And so when I just told you, when you just use the best point, that is this line here, you don't really reach the best performance you could get. The y-axis is a logarithmic scale and it's a distance to the actual best point. When you use, though, or model your yt here, two different methods for this. They're pretty similar, so I'm not going to go into details here. You actually manage to nicely get to the results you want to, but that's not so. I mean, it's a synthetic data, so that's not too impressive. We also applied it to a real-world problem at Plista. So the problem looks like we have a set of recommenders. We have n recommenders, and they all give us a list of recommendations, and we want to average them with a weighted average. So the task is to determine these W's. W's, of course, they should sum up to 1, should be bigger than 0. And as you see, so you can frame it as an optimization problem, as a reinforcement learning optimization problem, and this gives you a large Lagrangian that you can optimize for. You can actually find an analytic solution for it, and then you just have the problem that, yeah, again, there's non-stationarity, so you have to deal somehow to give all recommenders a chance to perform good. So the problem is that you easily run in local optima. So that's why it was an interesting task for us to compare it to the sequential model-based optimization, because it can be used for any kind of optimization. It doesn't have to use necessarily for hyperparameter optimization. You can use it to optimize essentially everything. And we managed to actually get a 3.3% lift up in the click rates. We didn't model directly W, we did model it at the declared distribution, and actually been looking for the alpha parameter of the distribution, because the W is constrained, so we couldn't kind of directly model it. And it worked out quite nice. Also, you probably ask yourself, do you have to implement it yourself? We're trying to get it into Mo currently. We send out a merge request, and we hope it's going to be available soon, so you can use it as well. Other problems, of course, I haven't mentioned this. The Gaussian process, when you train it, you have actually to inverse the kernel matrix, and this scales cubic with the amount of samples, which, of course, so it doesn't scale really well, but since you're only going to probably sample a couple of hundred instances, it's not a problem at all. And even if you would sample more, there are ways around it to approximate then this function. Also, of course, you introduce new hyperparameters, the hyperparameters of the Gaussian process, and but luckily they can be quite well inferred from the data, so you don't have to worry too much about it, and they don't have too many hyperparameters, depending on which kernel function you choose. And also, sadly, the optimization of the expected improvement function can be numerically quite unstable. Well, yeah, the values get really, really tiny. That can be a problem. Yeah, that's it. Thank you.
Thank you very much for your advanced talk. And we have time for some questions.
Hi, I'm really considering deploying Bayesian optimization for my deep learning models. But in the deep learning community, many people still prefer random search over Bayesian or other optimizations. For instance, undercut-Patik, which was mentioned 2 lectures ago. Nobody doubted the optimizations are working, but the question is whether they are worth the time, worth the costs. Especially when you consider the recent improvements like batch norm and additive gradients, which make deep networks much less sensitive to hyperparameters. So my question is, what would be your recommendation, or how do you cope with that, and whether these Bayesian optimization things are just I won't say marketing, but there are, Google ads popping at me all the time these days. So that's basically my questions regarding the optimization of deep learning models.
Yeah, so I mean, you said that it's kind of costly to use these kind of methods. And the question is, what do you mean by costly? Because basically you get that for free, right? You don't have, all you have to implement is for your language client to query the REST API of some existing libraries already, or you just implement them in your language and just call the function directly. So you don't have much to implement. Of course, if your model is very insensitive to the selection of hyperparameters, then well, you don't have to do it, right? That really then depends on what you're doing, but essentially you have to do so little to actually optimize it. And I mean, this is actually a global optimization search, right? So Yeah, I mean, it really depends on your task, so I can't really force anybody to use it. It's something you should just try it out once and see do you get actually a better result, and then that should be convincing to you. Just try it once and give it a chance, and if it's not better, then just don't use it.
Okay, so here's the question. Thank you very much for this talk. Can you show the plot with the hyperparameters as a function of time? You started the whole talk about. Yeah, that's it.
Yeah.
No, back. The plot, I mean. Yeah, that's it. Yeah. So that's over the whole week or.
This one?
Yeah.
Yeah, that's basically a little bit
Yeah,
more. Friday,
Saturday,
Sunday, Monday.
Yeah, okay. So maybe you said it, but I kind of drop it. So what's the time rate you use? How often do you update the hyperparameters?
Every 3 hours.
Every 3 hours. Okay, and but what you show is 1 week, and what's quite apparent is that there is a week periodicity.
Yeah.
So from 1 week to another week, the hyperparameter for a certain day, a certain time, can be quite lazy hyperparameter, right? That you have this week periodicity of these hyperparameters.
Weekend day, yeah.
So is it could be quite stable, right? So you.
Yeah, I mean, of course, we don't want to select different hyperparameters for different time points. We want to have just one hyperparameter for all of them. That's essentially. Of course, you could also then select different hyperparameters for different time points, but we haven't looked into this actually, but we've been afraid of overgeneralization actually, or overfitting.
Yeah, but where I'm heading is that it's kind of our model with, just time periodicity of 1 week.
Yeah, sure. You can integrate this kind of knowledge in the kernel function of the Gaussian process. There are periodic kernels, and there you can put periodicity in there and model that if you a priori know that that's how your data looks like.
Yeah, but still, very interesting. Thank you very much.
Would it be possible to implement a more analytical approach, namely gradient method where you select the random point and then you move in the direction where the function increases?
Sure, but then of course you might stuck in global optima, right? Global minimum.
Local optimas, you need to select several random points.
That's kind of the point about it, right? That you want to look for global optima, and that's why you need to search the entire space, or at least you search it dependently on how smooth basically your space is, right? And that's why with such an approach, it depends on how your data looks like, but you probably wind up not finding the best solution, I guess.
Hi, I have a rather factual question. You mentioned uplift of 3.33% of CTR. What was the subject of this uplift? Products on e-shop, news articles, or advertisement?
It clicks on the recommendations for other articles.
Okay. And the uplift, was it absolute or relative?
Relative. So this is our baseline approach that we used before by solving these Lagrangian